At 7:40 on a Tuesday morning, a ship turned sideways. That was all it took. The Ever Given was nearly 400 meters long, stacked with thousands of steel containers, and moving north through the Suez Canal. Then, amid poor visibility and high winds during a sandstorm, it veered off course, grounding with its bow in one bank and its stern against the other. The canal was sealed. Behind it, the world began to form a queue. Oil tankers, car carriers, bulk ships, container ships carrying furniture, machine parts, coffee, clothing, chemicals, and components for products that did not exist yet because one small piece was still at sea. More than 350 vessels waited. Some turned around and took the long route past Africa. For 6 days, a waterway that carries roughly 12% of world merchandise trade was reduced to the width of one stuck ship. And suddenly, something normally invisible became impossible to ignore. Those colored boxes were not just cargo. They were the moving parts of the global economy. But to understand how a plain steel rectangle came to hold that much power, we have to go back 70 years. Back to a converted tanker at a dock in New Jersey. Back to 58 boxes. Back to the day distance became predictable. This is the story of the box that built the modern world. Before the container, a port did not look like a giant game of Tetris. It looked like controlled chaos. A ship arrived carrying barrels, sacks, wooden cases, steel drums, baskets, crates, vehicles, coils of wire, and loose pieces of machinery. This was breakbulk cargo. Goods broken into individual loads that could be moved by human hands, hooks, nets, slings, carts, and small cranes. Every object had its own shape. Every shape created a new problem. A bag of coffee could be carried. Piano could not. A barrel might roll. A crate might split. A machine tool might weigh several tons and still need to fit through a narrow hatch. So the work happened one piece at a time. A gang on the pier lifted cargo into a net. A winch carried it over the rail. Another gang lowered it into the hold. Men below rearranged every piece, searching for a stable pattern inside a curved steel hull. Then, at the destination, the whole process ran in reverse. Loading and unloading could keep a ship in port for days, sometimes longer. Cargo was counted, checked, separated, stored, and moved again. Each handoff created paperwork. Each handoff created delay. Each handoff created one more chance for something to be crushed, soaked, lost, or stolen. The ship was often the fastest part of the journey. The port was where time disappeared. Cargo that would later move in one container lift could once demand 18 to 20 person-hours of handling. The precise burden changed with the commodity and the port, but the pattern was constant. More shapes meant more decisions, and more decisions meant more labor. Even the empty space cost money. A traditional ship had to be packed around beams, ladders, hatches, and the curve of the hull. Longshoremen were solving a three-dimensional puzzle, while the owner watched an expensive vessel sit still. One study by the shipping company Matson found that moving cargo between the pier and the ship could consume about half the total cost of transportation. For some goods, the journey across an ocean cost less than the few hundred meters across a dock. That sounds absurd. At the time, it was normal. For dock workers, it was also skilled and punishing work. They learned how loads behaved, how ropes tightened, how cargo shifted, and how to build a safe wall of irregular objects inside a moving ship. A mistake could destroy merchandise or kill someone. Ports developed their own cultures around this work. Hiring halls, unions, neighborhood bars, family traditions. A waterfront was not only infrastructure, it was a community with its own rhythm and language. And then there was the waiting. Truck drivers waited for cargo to be found. Trains waited for ships. Ships waited for berths. Factories carried extra inventory because no one could say exactly when the next delivery would arrive. The system worked. It had connected continents for centuries. But it did not scale easily. The obvious solution was to put smaller things inside a larger box. And people had tried. Railways used removable boxes in the 19th century. Military forces experimented with containers. Truck bodies were lifted onto ships. Small systems appeared in Europe and North America. So the shipping container was not one sudden invention. There was no single morning when nobody had a box, and one brilliant man drew a rectangle. The real breakthrough was harder. The box had to become part of a system. Malcolm McLean understood systems. He grew up in North Carolina, started with one used truck, and built a transport company by watching where money and time were being wasted. There is a famous story that, as a young driver in 1937, he sat at a dock for hours and suddenly imagined lifting his entire truck body onto a ship. It is a perfect origin story. It is probably not true. McLean began telling it much later, and the historical record does not support the neat moment of revelation. Real invention is rarely that tidy. What we do know is that, by the early 1950s, McLean was looking for a way around congested roads and expensive waterfront handling. He did not need to invent the metal box. He needed to make the box pay. His original idea was to carry complete truck trailers by sea. But a trailer includes wheels, axles, and a chassis. On a ship, those parts take up space and earn nothing. So the wheels stayed behind. The box would travel alone. That simple decision created a chain of engineering problems. How do you stack boxes in rough seas? How do you lift them quickly without bending the roof? How do you lock one box to another? How do you move the same box by truck, rail, and ship without opening it? Keith Tantlinger, a gifted engineer who had designed truck trailers, helped turn the idea into hardware. He developed stronger corner fittings and a rotating lock that could join a container to a crane, a chassis, or another container. The twist lock was small enough to hold in one hand. The consequence was planetary. Strength moved to the corners. The walls could be lighter. Cranes could grab the same points every time. Boxes could stack into rigid towers instead of sliding across a deck. In another demonstration, men climbed onto a thin aluminum roof and jumped. The roof held. Not every great engineering test looks sophisticated. McLean had another obstacle. American regulations separated trucking and shipping businesses, so he sold his trucking company and bought a small steamship line called Pan Atlantic. Then he bought 2 old T2 oil tankers from the Second World War. One was renamed Ideal X. Steel platforms were built above its deck. A crane was installed at Port Newark. And on April 26, 1956, 70 years ago this year, the Ideal X prepared to sail for Houston. On deck were 58 aluminum containers, the detachable bodies of truck trailers, built for the experiment. Their cargo was ordinary, and surviving accounts do not reliably record exactly what was inside. The way they were moving was. Observers stood on the dock. Some shipping executives were skeptical. Longshoremen had good reason to wonder what this machine would mean for their livelihoods. The crane lifted each box from a truck chassis, carried it over the rail, and lowered it onto the ship. About one box every 7 minutes. No sacks split open. No cases had to be res-tacked below deck. No one touched the goods inside. The Ideal X reached Houston in less than a week. The boxes were lifted onto waiting chassis and driven away. The demonstration had worked. And the numbers were brutal. Loading a conventional ship had cost about $5.83 per ton. Loading Mick Lane's containers cost about 15.8 cents per ton. About 1/37th as much, or roughly 97% lower. That famous comparison is often described as the price of shipping. It was not. It measured loading and handling at the port, not the total journey. But loading and handling had been one of the largest costs in the entire system. Cut that cost, and routes that had looked impossible began to make sense. The following year, a converted ship called Gateway City carried 226 containers. Unlike the Ideal X, it placed the boxes in vertical cells below deck. Before the Gateway City's first voyage, engineers pressed modeling clay into the cell corners. When the ship returned, the stacks had shifted by no more than 5/16ths of an inch. The experiment was becoming a network. Mick Lane renamed the business Sealand. The name was the business plan. There was still a problem. Mick Lane's box did not fit everyone else's box. Sealand used 35-foot containers. Matson, building its own system on the Pacific, chose 24 feet. Other operators used different heights, fittings, and lifting points. Imagine buying a charger that fits only one wall socket in one country, then making the charger weigh 20 tons. That was container shipping in its early years. A Sealand box might not fit a Matson ship. A crane designed for one system might not lift another. A railway car, truck chassis, or foreign port had to choose which private geometry it would support. Without a common standard, every network ended at the edge of itself. This is where the least glamorous characters in the story become some of the most important. Engineers, committees, regulators, shipping companies, railway representatives, people sitting around tables arguing over inches. In 1961, the International Organization for Standardization created a technical committee for freight containers. The negotiations were not simple. America had large roads and favored large boxes. European railways faced tighter clearances. Companies had invested in incompatible equipment and did not want their assets made obsolete. Mick Lane's 35-foot length did not become the global standard. The eventual system centered on 20-foot and 40-foot containers, with common dimensions, common corner fittings, and common strength requirements. In 1968, the first version of the standard, now known as ISO 668, formalized the main classifications and dimensions. Sealand also allowed crucial patented designs to be used royalty-free in the standard system. That decision mattered. A universal box could not depend on every port paying tribute to one company. The corner fitting became an international handshake. A box built in South Korea could be lifted by a crane in Rotterdam, locked to a train in Germany, transferred to a truck in Poland, and opened at a warehouse hundreds of kilometers from the sea. The people at each step did not need to know what was inside. They only needed to trust the corners. That trust produced a new unit of measurement, the TEU, or 20-foot equivalent unit. A 20-foot container counts as 1 TEU. A 40-foot container counts as 2. It is not a perfect measure. Containers come in different forms and ships are constrained by weight as well as space. But TEU gave the industry a shared language for capacity. Safety rules followed. The 1972 Convention for Safe Containers created international requirements for testing, inspection, and approval. Standards also created a powerful loop. Once several large ports bought standard cranes, shipowners had a reason to buy standard ships. Once shipowners bought those ships, railways and trucking companies had a reason to buy matching equipment. Every new participant made the system more useful to the next. The box succeeded partly because it stopped belonging to any one inventor. By then, the rectangle was no longer just a product. It was a protocol. And protocols become powerful when nobody has to think about them. Containers save time. But time was somebody's job. On the old waterfront, hundreds of people might work a single ship. They moved cargo, sorted it, checked it, guarded it, and repaired the damage. Containerization removed entire stages of that process. A crane operator could lift a sealed box in minutes. The work inside the box had already happened somewhere else. Dockworkers saw what was coming before most of the public did. They did not simply reject technology. They fought over who would receive the benefit and who would absorb the cost. On the American West Coast, the 1960 Mechanization and Modernization Agreement gave employers greater freedom to introduce labor-saving equipment. In return, the union secured income guarantees, early retirement support, and a fund worth roughly $29 million. It was an attempt to bargain with the future. Even with protections, the workforce shrank. Later international estimates found that containerization eliminated between 40 and 60% of port jobs in many places. The jobs that remained changed. Some became safer, more technical, and better paid. Others disappeared with the cargo sheds. The human cost cannot be captured by a chart alone. A job lost on a waterfront could mean a family leaving the neighborhood, a shop losing customers, a skill passed from one generation to the next no longer having a place to go. The geography changed too. Old ports had grown beside city centers because cargo needed people, warehouses, and short distances. Containers needed something different. Land. Enormous, flat areas for stacking boxes. Deep water for larger ships. Strong road and rail connections. Giant cranes. Turning space. Historic waterfronts often had none of those things. New York's traditional piers in Manhattan and Brooklyn began to lose cargo to New Jersey, where there was room to build. On August 15, 1962, the Port of New York Authority opened the first part of a vast container terminal at Elizabeth. The center of gravity crossed the harbor. Warehouses and trucking companies followed. Old piers fell quiet. Some were abandoned. Others were eventually reborn as parks, offices, apartments, and tourist districts. The same pattern repeated elsewhere. Oakland gained an advantage over San Francisco because it had flat land and direct rail access. Around the world, successful ports moved away from old urban cores and grew into specialized landscapes of asphalt, lights, fences, and cranes. In 1966, Sealands Fairland crossed the Atlantic to Rotterdam with containers. The box was leaving its American test ground. Now it needed the world to rebuild around it. The system's most important early test came in a place where delay had consequences far beyond profit. Vietnam. By the mid-1960s, the United States was trying to supply a rapidly expanding war across the Pacific. Ammunition, vehicles, construction material, medicine, and food arrived in quantities the existing ports could not handle. Ships waited offshore. Cargo piled up. Records failed to match reality. Some supplies were damaged by rain. Some were stolen. Some simply could not be found. A crate might cross an ocean, reach the right country, and then vanish into a mountain of other crates a few kilometers from the soldiers who needed it. In 1966, Malcolm McLean offered the government a package: ships, containers, trucks, cranes, and a managed flow from origin to destination. Again, the product was not the box. The product was the system. New container facilities were developed, including at Cam Ranh Bay. In October 1967, the first container ship entered the Army terminal at Newport near Saigon. Military accounts reported that a container ship could be unloaded as much as 10 times faster than a conventional cargo ship, with fewer workers, less damage, and less theft. A sealed container could leave a factory or depot in the United States, cross the Pacific, and continue inland without its contents being handled at every transfer. It was logistics made legible. Commanders could count boxes. Planners could schedule cranes. Truckers could take a complete unit and move. The container did not make war clean or simple. It made supply more reliable. By late 1967, one of the strangest measures of that change was visible. Refrigerated sealand containers were delivering fresh produce at scale. Lettuce, pears, tomatoes, melons. Inspectors opened the boxes in tropical heat and checked the temperatures. A technology built around steel and diesel had created a cold corridor across the Pacific. For soldiers eating preserved food, a fresh salad was a small thing. Logistically, it was astonishing. The box could now carry its own climate. Then Mick Lane found cargo for the return journey. Ships that crossed the Pacific full of American supplies could stop in Japan and load manufactured goods, including electronics, for the United States. By 1968, the wartime route was becoming a commercial triangle: America to Vietnam, Vietnam to Japan, Japan back to America. War did not invent containerization. The Ideal X had sailed more than a decade earlier. But the war provided what the young system lacked: enormous demand, government money, new terminals, and no tolerance for delay. It proved that containers could operate across an ocean at massive scale. And when the war ended, the ships, ports, routes, and habits remained. Once the standards existed and the ports were built, the box began to change more than shipping. It changed what companies believed was possible. Before containerization, making a product far from its customer carried a heavy penalty. Ocean freight itself might be cheap, but handling was slow and uncertain. Inventory could be lost. Deliveries could arrive weeks late. Every border between truck, train, dock, and ship created friction. The container turned those separate journeys into one movement. A factory could load a box, seal it, and send it through several modes of transport without unpacking the cargo. Documents traveled with the shipment. Schedules became more reliable. Theft and damage fell. Most importantly, managers could plan. Distance had not disappeared. It had acquired a timetable. In the United States, the 1980 deregulation of rail and trucking allowed transport companies to change routes, rates, and services more freely. Double-stack trains carried containers inland. Computers tracked bookings. Barcodes improved identification. Electronic documents replaced part of the paper chase. The box was the physical core, but it worked because other systems grew around it. Ships, cranes, rails, highways, trade rules, insurance, finance, software. Globalization was not built by one object. The object made globalization easier to organize. Companies began separating production into stages. A product could be designed in one country, use raw materials from another, contain components made in several more, be assembled somewhere else, and sold almost everywhere. By the 21st century, these global value chains accounted for nearly half of world trade. The label "Made in" became less a complete answer than the first line of a very long story. Consider a smartphone. Its minerals may come from mines on several continents. Its chips may be designed in the United States, fabricated in East Asia, and packaged somewhere else. Its screen, camera, battery, casing, and circuit boards follow different routes before meeting at an assembly plant. The finished device feels singular. The supply chain is a map. And at many points on that map, there is a box. The transformation also changed time inside the home. Retailers could order seasonal goods from across an ocean and expect them within a planned window. Supermarkets expanded what they sold. Manufacturers reduced the number of parts sitting beside the assembly line. Consumers became accustomed to products that were cheap, varied, and available almost immediately. That expectation now feels natural. It is engineered. Behind the click of a buy button sits a chain of bookings, cranes, customs filings, chassis, warehouses, and people working through the night. The container hides that complexity so well that we notice the supply chain mainly when it fails. No country reveals this transformation more dramatically than China. In 1980, Shenzhen was designated as one of China's first special economic zones. It offered a place to experiment with foreign investment, export manufacturing, and market-oriented policy. Shenzhen also sat beside deep water and close to Hong Kong. Factories multiplied. Ports expanded. Roads, power, and logistics networks followed. Then, on December 11, 2001, China joined the World Trade Organization. Containerization did not cause China's rise on its own. That story also includes policy reform, a huge workforce, foreign capital, education, infrastructure, currency choices, and access to consumer markets. But the container supplied the physical mechanism. It made it practical to connect an inland factory to a shelf on the other side of the planet. In 2000, China exported about $249 billion in goods, roughly 4% of world merchandise exports. By 2007, the value was approaching 5 times that level. Ports such as Shanghai, Shenzhen, Ningbo Zhoushan, and Qingdao expanded at a speed that would have been difficult to imagine in the age of breakbulk cargo. By 2019, 16 of the world's 20 leading container ports were in Asia. 10 were in mainland China, Hong Kong, or Taiwan. The map of trade had tilted. Economists have tried to measure how much the container itself mattered. One model estimated that containerization produced a cumulative increase of roughly 700% in trade between industrialized countries over its first 2 decades of adoption. That is an estimate from an economic model, not a count of boxes and not proof that one technology acted alone. Another Federal Reserve study estimated that being within 100 kilometers of a containerized port increased a county's population by about 70% over the 60 years from 1950 to 2010. The exact numbers depend on the method. The direction does not. Places connected to the new network gained opportunity. Places bypassed by it often lost ground. The box made the world smaller. It did not make the world equal. For consumers, containerization often arrived disguised as abundance. More choice. Lower prices. Products from far away becoming ordinary. Bananas in winter. Flat pack furniture. Fast fashion. Electronics assembled from hundreds of specialized parts. The cost on the price tag fell. Other costs moved out of sight. First came the industrial dislocation. When transport became cheaper and more reliable, companies could move production to places with lower wages or different regulations. Some regions gained factories and millions of jobs. Others lost industries that had anchored communities for generations. The container did not make those decisions. People, companies, and governments did. But it changed the menu of choices. A factory no longer had to be near its customers. It had to be near a reliable route into the network. That freedom increased efficiency. It also increased the bargaining power of capital over workers and places. Then there is the environmental cost. Shipping is efficient when measured per ton of cargo moved over a long distance. A large vessel can carry an extraordinary amount of freight with less fuel per ton than an aircraft or a truck. But efficiency per unit is not the same as no impact. In 2018, shipping emitted about 1.056 billion tons of carbon dioxide, equal to roughly 2.89% of global human-caused carbon dioxide emissions. That figure covers shipping as a whole, not container ships alone. And climate change is only one part of the bill. Ships burn fuel near coastal communities. Trucks and locomotives converge on terminals. Cranes, warehouses, and distribution centers operate around the clock. Noise and air pollution fall heavily on neighborhoods beside ports and freight corridors, where residents are often poorer than the national average. The clean rectangle on a shop floor can cast a dirty shadow somewhere else. There is waste too. Trade imbalances send full boxes in one direction and empty boxes back. Containers pile up where demand is weak and become scarce where exporters need them. Repositioning empty equipment consumes money, land, and fuel. And the box creates a peculiar kind of anonymity. A sealed container is trusted precisely because nobody needs to inspect every object inside it. That makes trade fast. It can also conceal counterfeit goods, dangerous cargo, drugs, weapons, trafficked wildlife or people.
Port façon impossible arithmétique.
Inspect every box and global trade stops. Inspect too few and the network can be exploited. The system depends on selective trust. So does almost every system at this scale. For decades, businesses learned to remove slack. Warehouses became smaller. Inventories became thinner. Components arrived just in time for production. Why pay to store a part for a month when a ship can deliver it on Tuesday? It was a beautiful calculation. Until Tuesday changed. In March 2021, the Ever Given turned sideways in Suez. Factories waiting for components slowed. Retailers watched delivery dates slip. Freight rates moved. Ships burned extra fuel sailing around the Cape of Good Hope. The vessel was freed after 6 days. The disruption lasted much longer. And Suez was only one warning. The pandemic closed factories and terminals, while consumers shifted spending from services to physical goods. Containers accumulated in the wrong places. Ports became congested. In 2023 and 2024, attacks near the Red Sea pushed ships away from Suez again. Drought restricted transits through the Panama Canal. Each shock had a different cause. The lesson was the same. The network was efficient because it was tightly connected. It was fragile for the same reason. We built the system to waste almost nothing. That included time, warehouse space, and room for mistakes. One missing component can stop an assembly line. One closed terminal can rearrange routes across an ocean. One ship in the wrong position can become a cork in the neck of the world. This does not mean global trade is ending. It means the definition of efficiency is changing. The cheapest supply chain on a calm day may be the most expensive one during a crisis. 70 years after the ideal X, the box is still evolving. Modern container ships can carry more than 24,000 TEU. The ideal X carried 58 experimental boxes. Those figures are not directly comparable. Mick Lane's original containers were longer than a 20-foot unit, and the modern TEU did not yet exist. But the scale of the change is still difficult to hold in the mind. 58 boxes on top of a converted tanker became floating cities of steel. The boxes themselves are becoming more visible to the systems around them. Sensors can report location, temperature, humidity, shock, and whether a door has been opened. Electronic seals can show signs of tampering. Refrigerated containers can warn an operator before a cooling unit fails. Ports are automating gates, cranes, and vehicles. Better data can reduce the time ships spend waiting and the fuel they burn. Digital documents can replace slow, vulnerable chains of paper. Yet more connection also creates new risks. A cyber attack can interrupt a terminal without touching a crane. A false data point can send a box to the wrong place. A smart container is only useful if different companies and countries can trust the information it shares. Once again, the challenge is not just invention. It is agreement. Shipping also faces the hardest redesign in its modern history, moving away from fossil fuel. The International Maritime Organization's current strategy aims for net zero greenhouse gas emissions from international shipping by or around 2050. No single replacement has won. Methanol is moving first on some routes. Ammonia and hydrogen may play roles if clean production and safe handling can scale. Batteries can serve shorter distances. Wind assistance, improved hulls, slower speeds, and cleaner port power can reduce fuel demand. Every option has trade-offs. The next global standard may not be the shape of a box. It may be the fuel in the ship carrying it. Governments and companies are also reconsidering where goods come from. Some production is moving closer to consumers. Some supply chains are adding second suppliers, larger inventories, and alternative routes. But resilience is not the same as retreat. An economic model from the OECD found that wholesale relocalization could cut global trade by more than 18% and global output by more than 5%, without consistently making economies more stable. A network can be made safer without tearing it apart. More routes. More suppliers. Better information. Strategic reserves where failure would be catastrophic. The goal is not a world without connection. It is a world with options. Look at a shipping container and there seems to be almost nothing to see. Corrugated steel. 2 doors. 8 corners. A number painted on the side. That plainness is its genius. The container does not care whether it holds coffee or computers. The crane does not care where the box was packed. The ship does not need to know who will open it. Each part of the system performs one simple action, then passes the box forward. The miracle is not the metal. It is the agreement. An agreement on dimensions, on corners, on locks, on documents, on schedules, on the promise that a box sealed in one place can move through hundreds of hands without being opened. That agreement created extraordinary wealth. It also erased jobs, shifted cities, spread pollution, enabled offshoring, and tied distant lives together so tightly that a blockage in Egypt could delay a factory in Europe and empty a shelf in America. The box did not invent globalization. It gave globalization a body. And like every powerful technology, it carries the values of the people who build the rules around it. Efficiency or resilience. Low prices or hidden costs. Speed or safety. Connection or dependence. Those choices were never made by the box. They are ours. On April 26, 1956, the Ideal X left New Jersey with 58 containers. No one on that dock could see the full chain of consequences. The new ports, the global factories, the megaships, the fresh food crossing oceans, the old waterfronts going quiet, the canal blocked by a single wall of steel. They saw boxes. We can see the system. The box did not erase distance. It made distance predictable. And once the world learned to trust that prediction, it rebuilt itself around it.